to another concept of acids and bases that you may or may not be familiar with. You may have, we may have learned it in high school when you took chemistry, if you took chemistry, but maybe not. So let me introduce you to first the idea of what we call a Lewis acid. And a Lewis acid is basically an electron acceptor. Right? Sometimes you'll also see it referred to as an electron pair acceptor. Right? So any atom or ion that can accept electrons, we call it a Lewis acid. And many times your Lewis acids are going to be metals. So some metal ion, like say magnesium 2+, copper +1, cobalt 3+. It just, those are what we call Lewis acids. They can accept electrons from other atoms, all right, or from other ions, right? It's not always going to be a neutral atom. Sometimes it'll be from an anion, or sometimes it'll be from a neutral atom. So it just depends, right? And then when you think about other types of Lewis acids, metalloids kind of qualify. Some of them do. Can also be Lewis acids, right? Something like silicon, boron, metalloids that fall into that category. And the way Lewis acids accept electrons is they accept electrons into empty orbitals. Right? So we haven't talked much about orbitals. That's coming up, but an orbital is simply it's just a location of electrons within the shell or the shells of a particular atom or ion. We're going to talk about all of this later. I'm sure you've heard of it. If you took high school chemistry, you know what about shells and electron configuration and all that, but we just haven't gotten to that yet. So atom or ion has electron shells or orbitals or in those shells. And if an orbital is empty, it can take a pair of electrons. So Lewis acids have some empty orbitals somewhere where they can receive a pair of electrons from another atom or ion. And then we have Lewis bases, which is what a Lewis base is basically the counter to a Lewis acid. So it is an electron donor. It's an electron donor. So any atom or ion that can donate electrons will be considered a Lewis base. Any atom or ion that has a lone pair, or even in some cases a polarized bond, but mostly you'll see donation coming from what we call lone pairs. It will be considered a Lewis base. So something like this. Let me put that in here. Any element or ion with a lone pair can be a Lewis base. Right? So Lewis bases are not, this is a different idea, a different concept of acids and bases. We're not going to spend a lot of time here, but I just wanted to introduce you to it because you're going to see it again. And so an example of a Lewis base, a couple of examples, if I have something like this, would it have a negatively charged carbon? So I have a carbanion. You know, the anion is for negative. The carb is for carbon, so it's a carbanion. Or if I had something like ammonia with a lone pair, you see the lone pair of electrons here. Those are Lewis bases, right? An example of a Lewis acid, Lewis base relationship would be here, right? If I had something like I had something like acetone, right? This oxygen right here with these lone pairs would be considered Lewis basic, right? And then if that oxygen donated a pair of electrons to an atom like, let's say, copper, right? Then the copper in this case, let's say copper +1. Then the copper in this case is going to be what we call Lewis acidic. Right, so it's a little bit different than the concept of Lewis. I mean, I'm sorry, acids or bases that we're used to. Right, so Lewis acid is an electron donor. Lewis base, Lewis acid is an electron acceptor. Lewis base is an electron donor. All right. So now we're going to shift gears and talk about the traditional concept of acids and bases, which we know as what we call Bronsted acids and Bronsted bases. Right. So let me introduce the acids first. We're going to talk about some other elements that let me not say elements, some other pieces to this concept as well when we talk about acid-base reactions. But the more traditional definition of an acid that we think of commonly is what we call a Bronsted acid. Right now, and a Bronsted acid is what we call H+ donor. H+, we commonly call this a proton, because if it's a hydrogen ion that has lost one electron, so the only thing that's left is the proton that's in the nucleus. So we call it a proton. So if a proton donor, that's what a Bronsted acid is. It gives away H+, so it'll have a proton somewhere that's able to be donated to what we call a Bronsted base. So a Bronsted base is a proton acceptor, right? So Bronsted bases react with Bronsted acids to transfer protons between them. So anytime you have an acid-base reaction between a Bronsted acid and a Bronsted base, there's going to be a proton transferred somewhere. Right now, don't get this term proton confused with the subatomic particle. If there's a proton transfer in an acid-base reaction, it's the actual atom, the actual hydrogen ion, right? So protons are transferred from the acid to the base. So that's what happens in an acid-base reaction, right? So let me give you an example. So you could have, let's just say, for instance, you have an acid, let's just say HA, a generic acid. And then you have a base here with a negative charge. Not all bases are negative. Some can be neutral. But let's say you have a acid and a base and you react them together. Typically what happens is this proton right here, I'm going to highlight it. That proton is going to be transferred to the base, right? The base is going to use that pair of electrons, because all bases have to have electrons in order to pick up a proton. You can't pick up a proton or accept a proton without some electrons to give it, right? Because remember, it's coming as H plus, so it has no electrons. So normally what happens is you would draw an arrow from that pair of electrons on the base to pick up the proton. And then this bond right here, we break it and give the electrons in that bond to A, because remember, well, maybe not, we haven't really talked about bonds yet, but when we have a bond between two atoms, let's just say X and Y, that bond is, if it's covalent, anybody remember what that term covalent means?
Ain't it like a double bond or a single bond?
Yeah, it's a single bond, that's true. And the way you make it is you share electrons. So a covalent bond is a bond that has shared electrons. And every bond, when we think about a bond, a covalent bond between two atoms, every bond consists of two electrons between those atoms, right? So every covalent bond is composed of two electrons. All right, so let me not just say all bonds, let me say all covalent bonds, because I want that to be clear. So all covalent bonds are composed of two electrons, right? So the bond that I'm going to make between H and the base is a covalent bond, and it's made by those two electrons from that base being donated to hydrogen. And then I'm also going to break that HA bond, so I'm going to be left with A with two electrons on it, and more than likely a negative charge. Right, so that's just a generic acid-base reaction where you have the acid plus a base. And then on the other side, let me give you this term too, excuse me. You have what's called a conjugate acid. Highlight that. And then A becomes what we call the conjugate base. right? So acid is over here. This is the acid. And then this is my base. Obviously, it's called base. And then on the other side of the arrow, you have your conjugate acid and your conjugate base. So this is a basic example of what we call proton transfer, right, between the acid and the base. Right. Any questions about that? So this is what happens when you react acids and bases. That's how protons are transferred. The base supplies a pair of electrons. The acid gives up a proton, and everybody's happy at the end. All right, let me actually move this. Hold up. That's why I kind of, I was just about to brag on that, but maybe not now. All right. So this is a basic proton transfer. This is what happens when you take acids and bases and you react. All right, so let's talk more about acids. And what we know about acids is that a few things. If it's a strong acid and you dilute it or add water to it or add it to water, because you always add acid, not add water. If you add the acid to water to dilute it, it's going to completely dissociate. Can anybody tell me what that term dissociate means? Right, what does it mean for something to dissociate? Right, think about this in terms of two ions being together. Right, so you'll have let's say you have a compound XY, and then when you dissolve it in water, it becomes X plus and Y minus, right? We did this already when we looked at those ionic equations. So when we say something dissociates, that's what we mean, that it is broken up into its constituents. All right. And if it's a strong acid and you dilute it, then it's going to completely dissociate. So if I have something like this, so I have something like this is an example. So if I have sulfuric acid, when I add that to water, it's going to become the protons from the acid plus the sulfate anion. Right? So that's what we mean by dissociation. Weak acids don't dissociate like that. They don't dissociate. They only partially dissociate. So we can add that into this as well, this description of acids. So a weak acid is only going to partially dissociate when you dilute it. All right, so another example would be to take HCl, which is a very strong acid. And I'm going to show this two ways. All right, so we take that plus water. Water in this case can act as water is what we call amphiprotic. Right, what that means is that it can be an acid or a base, depending on the conditions. So it can act as either or. But in this case, with HCl, this is my acid. So water in this case is going to act as my base, right? And let me write this out like I did for the morning class so we can get in the habit of seeing what's happening. So this is what the structure of water looks like. Bent geometry, 2 lone pairs on oxygen. And so when this reacts with, or when you add HCl to water, you get a couple of things, right? First, you get HCl ionizing or dissociating, right? And then, of course, chlorine. Let me put this in here. Chlorine has 4 lone pairs of electrons around it. And we'll talk about why. Over here, it has 3 lone pairs, right? So when water as a base donates that pair of electrons and plucks off the hydrogen, the electron here is going to break. I'm sorry, the bond there is going to break between H and chlorine, and you're going to get the chloride anion on the other side. Sloppy. Right? So that's where that other pair of electrons comes from. Over here. Comes from that bond. Right? But also you can think about this in terms of the acid base aspect, where you have Cl minus, right? And then plus H3O plus, right? Because it's water that picks up that hydrogen. Let me highlight it. It's water that picks up this hydrogen. So I'm gonna put it right here. So water becomes H3O plus, acting as your base, right? And so that proton gets transferred to water. This is what we call a hydronium ion. Right? And anytime water is acting as a base, the hydronium ion is going to be formed, right? In this reaction, if I have my acid and my base labeled, which one of those on the product side, which one would you label as the conjugate base? The conjugate base. If the acid loses a proton, it becomes the conjugate base. So look at the acid, it's HCl. On the other side, you have H3O plus and Cl. So which one of those is the conjugate base? Right, it's going to be this one. The conjugate base is always what's left over after the acid loses or transfers that proton from itself. And then by default, the base on the left side of the arrow, when it picks up a proton, it becomes the conjugate acid. Right, and that's important because this reaction is actually in equilibrium. So there's an equilibrium between the products and the reactants, and the extent of equilibrium is going to depend on what the conjugate acid is and what the conjugate base is. All right. So that's for a strong acid. If we think about a weak acid, like acetic acid, all right? Let's show that reaction. So acetic acid is here. Right? And acetic acid is a weak acid. What that means is that when it's dissolved up in water, it doesn't, excuse me, it doesn't fully dissociate. This pollen is killing me. It only partially dissociates. All right. So it's a weak acid and it partially dissociates. Right. Only about 1% of that acetic acid is going to actually ionize or dissociate. Right. So here I'm going to take this and let me move this. I'm gonna react this again with water because I'm using water as my base. All right, same process. Water is gonna come and pluck off that proton. And that pair of electrons in the OH bond are going back to oxygen. So on the other side of the arrow, which is in equilibrium, we'll talk more about that later. You have this as your conjugate base. That's negative. And then you have this as your conjugate acid. All right, where it picked up that proton. Right, this ion, we've seen this before. This is the acetate ion. Sometimes you'll see it written like that. The other day when we were talking about it, we saw it written like this, C2H3O2 minus. Or you can see it written like this, CH3COO minus. But all of it is the same. It's the acetate ion. It's one of the polyatomics that we studied earlier. All right, so this is a weak acid dissociating in water. And then the equilibrium part, let's talk about that. If it's a weak acid, more than likely, the equilibrium is going to favor the reactants. So this is the reactants on the left, and on the right, we got products. Right, so when you write your equilibrium arrows, you can actually write them like that, showing which side is favored. You see how the top arrow is longer than the bottom arrow? That means that the substances on the left are favored over the substances on the right. So you think about this, like I mentioned to the class this morning, if you think about this like a seesaw, the seesaw will be tilted this way to the reactants. All right, and we'll talk more about this, especially in organic with acids like acetic acid, because this is what we consider an organic acid. Right, it's not like the acids like HCl and HBr and HI. This is an organic acid, meaning that it's carbon based. Right, you can see that there's carbon in the structure here as well as here. Right, so any carbon containing molecule, we call it organic. That's why that's a totally different sub-discipline of chemistry. Right, you have general, then you have organic, analytical, physical, all these other sub-disciplines. So organic chemistry is not like organic as we think of, like, buying organic tomatoes or whatever. It's literally the study of carbon-based molecules and how they react. All right, so with that said, let me give you some strong acids, typical strong acids. HCl is an excellent example of a strong acid. And again, by strong acids, what we mean is that it's a compound that will dissociate fully when it's dissolved up in water, right? So HCl, if I add this to water, I'm going to get H plus Cl minus, right? It's going to fully dissociate. Same with HBr, I'm going to get the same thing, H plus Br minus, right? All strong acids fully dissociate when they're in solution, right? When they're in solution with water. HI, same thing, H plus I minus. And then of course you have other acids like nitric acid, which if you dissolve it in water or you make a solution out of it, it's going to ionize to H plus and then NO3 minus. Right, sulfuric acid. I think y'all when y'all did the acids and bases lab, did we use sulfuric acid? I can't remember. It'd be 2H plus SO4 minus 2, right? And this sulfuric acid is really like a very strong acid and nasty. Get it on your skin, you'll know it. And then you have H3PO4, which is phosphoric acid, and that's going to dissociate here, 3H plus PO4 minus 3. All right, so this is phosphoric acid, sulfuric acid, nitric acid, hydroiodic acid, and then hydrobromic acid, and then hydrochloric acid. Right, same HCl is the same as stomach acid. That's the acid that's in our stomachs that helps to break down the foods that we eat. All right. I want to start bases, but I'll wait until tomorrow. So we'll start like bases. We'll do a little bit of acid base neutralization reactions, and then we'll start on redox chemistry. So we'll do that tomorrow. And then on Monday, we'll probably do stoichiometry, and then Wednesday, titration, and we'll be ready for our next test on Friday. So next Thursday, that's when we'll have another recitation handout that we'll work through. And there won't be as many problems. It'll be 1 or 2 problems from every section, so we can knock it out in one session. Then you'll turn in that plus the last handout on the when you take or after you take the exam. All right, we got to stop there. It's 1:48, and I want to start bases and then run out of time. So we'll stop here.